Okay, so in this video, we're going to cover the ERM triangle and then the special cases. So this is the lecture that we gave week 2 of electronic navigation. So as I said, we're going to cover the ERM triangle and special cases. All right, so let's say you had a target at this range and bearing at time 0, r, and then a second range and bearing at m. So this would be your relative motion line. And the CPA would be a 90-degree angle from your relative motion line, okay, to the center, right? And let's say here we're making 20 knots, and we're going 0, 0, 0. So there's our heading line. So if we're making 20 knots, in 6 minutes, we're going to go 2 miles, okay? 6 minutes is a tenth of an hour. So a tenth of 20 knots would be 2. Okay, we just move that decimal over. So what I'm going to do now is I'm going to put a vector onto r that's going to represent my motion. Okay, so since I'm going 20 knots in 6 minutes, I'll go 2 miles. So you can see here, if I'm going north, I would go 2 miles in that 6 minutes. But I'm not going to put the vector there. I'm going to put it over here towards r. All right, so I'll measure 0, 0, 0. And then slide it over to r, and I'm going to draw a line towards r that is 2 miles long on this scale. Okay, I'm going to label that spot E. Okay, so I've done that. Now, the next thing I'm going to do is if I connect E and M, I close my triangle. Okay, and so I'm going to do that. All right, and if this vector here, this is the relative motion. All right, a combination of my motion and the target's motion. This is my true motion. This is the vessel's true motion. So this is a vector. E to r is our. E to m is them. So the orientation of that in degrees is their true course. And the length of that, okay, is going to be their speed. Now, this is their speed in this is their distance in 6 minutes, okay? So I'll be able to use that 6-minute rule in just a minute to get their speed in just a moment. So, but anyway, this is the orientation of it. If I take my triangle and I bring it to the center, looks to me like their true course is about 248. Okay, and let's see, and their speed, if I measure that distance, okay, in 6 minutes. And you can see, by the way, if this is 20 knots, they're going to be going 35 or something like that, because that line is much longer than mine. I come over here and I measure it, and it looks like to me like that is 3.1 miles in 6 minutes. So I multiply that 10, and that tells me they're making about 31 knots. So their true course is 248 according to my plot, and their true speed is 31 knots according to my plot. Now, in actuality, due to some errors in my plotting, their course might be a little more, a little bit less. Their speed might be a little bit more, a little bit less. But this is the general idea. Okay, so let's just review here. R was the observation of the target at time 0. M is the observation of the target at time 6. Okay, we're using 6 minutes so that we can use the 6-minute rule to easily move our decimal back and forth to convert from distance to speed and speed to distance. And the legs of our triangle are E to R, our, or we are, own ship's true course and speed. E to M, them, the target's true course and speed. And R, M, that's the relative motion line. Okay, so these are actually ER and EM are vectors. RM is a resultant. Okay, so now I'm just going to run you through some little scenarios here, and we're going to answer these questions as we go along. All right, and you were given this handout in class. So in all these situations, we're going to be going 0, 0, 0 at 20 knots. All right, so here's R, here's M. So my relative motion line from R to M, I can draw it right through the center. And if I want to know the direction of my relative motion, I'll just extend this line across. And it looks to me like my direction of relative motion should be about 220. So what's the speed of the relative motion? Well, to get the speed of the relative motion, I'm going to measure the distance that the target appeared to move, that the target, the motion of the target on my screen in 6 minutes. What was that distance from this time to this time? Okay, and if I take my dividers and I bring that over here, it looks to me like that was 3 miles in 6 minutes. Okay, so I'm going to move the decimal over 1. So it's 3. I'm going to move the decimal over, making the number larger, and it's 30 knots is the speed of relative motion. Now, neither myself nor the target are going 30 knots. Neither myself nor the target are making 220. That is the relative motion. So now I want to figure out the CPA. So the CPA looks to me like the CPA is going to be about 0 based on this plot. So there's a CPA, so that's 0. And then I want to know, when is that CPA going to happen? So if it was 6 minutes to go 3 miles, well, another 3 miles is another 6 minutes, and another 3 miles is another 6 minutes. So I can kind of just walk this down in 6-minute increments based on the length between R and M. So I would take my dividers, I get that distance, and I start walking it down. So that would be 12, 18, 24, but it's a little bit less than 24. Looks to me like it's a third less, so that would be CPA should be in about 22 minutes from the time of R. Okay, so if I made my observation at noon by the clock, it would be noon at 22 minutes past noon would be when the CPA would happen. Okay, so now what I want to do is I want to get the true course and speed of the target. In order to do that, I'm going to plot my true course and speed. So I'm going 0, 0, 0 at 20. If this is a 6-minute time frame here, I'm going to take 20, I'm going to move the decimal over 1, and I would go 2 miles in 6 minutes. So I'm going to measure 2 miles over here, and then I'm going to take that line, and I'm going to draw it towards R. And that's what I just did. And I'm going to label the beginning of it E. So E to R is hour, that's my vector. R to M is the resultant. Let's pull out the other vector. The only thing remaining, E to M, is them. And I just draw that, okay, right on there. And now, if I want to get the orientation of that and the magnitude of that, that will be my answers here. Okay, so first of all, just let's notice that this line is about the same length as that line, which means our speeds are about the same. And this line is about, anyway, so let's go ahead, we'll take our triangle. Okay, if we put our triangle there, that's, and we bring that down to the middle, then I don't have the triangle in this image, but you get the idea. I take that direction, I bring it to the center, and now it's oriented to the outer scale. And it looks to me like the true motion is 260, and their speed should be about 20 knots. If I measure with my dividers and bring that over here, I can get that exactly, and that's 20 knots. Now, just notice here as well. This is our heading. This vessel's in our starboard bow. It has a CPA of 0. We are the burden vessel. We are the vessel that needs to alter course. And we'll deal with that in a few slides from now, where we'll figure out what a new course should be that we should steer. Okay, so that is the ERM triangle with a CPA of 0. Okay, let's do another situation. Now we're getting into what are called the special cases. So in this case, if I had R and then M, okay, that is the relative motion. All right, the direction of relative motion, if I could just connect R to M, all right, looks to me like the relative motion is, if I was to use my triangle, I would take this line, I would bring it over here to the middle, and the direction of relative motion would be 180. Okay, great, I got that. What's the speed of relative motion? All I have to do is measure the distance in 6 minutes that I went, and then multiply that by 10. So I'm going to measure with my dividers from here to here, and that'll pop up over here as about 1 mile in 6 minutes. I multiply 1 times 10, and that tells me that the speed of relative motion is 10 knots. So what's the CPA? Well, the CPA is going to be a line, the CPA should happen right about here, but if I want to know exactly, I'm going to draw a line from the center that intersects my relative motion at a perpendicular angle, a 90-degree angle. So that is where the CPA will happen right there. And now I can measure that distance from here to there with my dividers. If I set my dividers and then bring them over here to my scale, again, I'll be 7 miles. By the way, every one of these images, the radar was set for 12-mile scale. Therefore, I'm going to use the 12-mile scale provided on my radar plotting sheet. Okay. So that was that. So CPA is 7 miles. Now, what's the TCPA? Well, if that's 6 minutes, that should be 12, 18, 24, so on and so forth. And we just walk all that down with our dividers, and it looks like it's a little bit less than 48. So it's 47 or 46. I'm going to say 46. Okay, so if my first observation of R was at noon, then the time of the CPA would be about 12:46. Okay, now let's figure out the true motion of the target. In order to do that, I'm going to take my motion, and I'm going to add it to the R, to this R here. So I'm going 0, 0, 0 at 20. So I take my 20, I move my decimal over 1, and I'm going to go 2 miles in 6 minutes. So that's E to R. So I'm going to draw that line over here towards R. And when I do that, okay, really it would be over on top of this, but I've drawn it to the side so you can see the color. This is the spot that's going to be E right here, okay? So E to R is our, okay? And now you can see that there's no triangle, okay? And so this is what's referred to as a special case. When the triangle collapses into a line, we have a special case, and there are 5 of them. So let's figure out what the true course and speed is of this vessel. So to get that, I'm going to go from E to M, okay? So E to M right here, okay? E to M right there. So they're going north, okay? That's north, 0, 0, 0. And the magnitude of E to M, if I bring that over here and measure it, that's 10. That means they went, excuse me, that's one nautical mile in 6 minutes. I just move the decimal over 1, and I get my speed of 10, okay? So this is no triangle, a special case. And the special case is same course, but in this case, E to M is them, and E to R is our. We're going faster. As a matter of fact, we're going twice as fast as they are, okay? But this is a special case where we are overtaking, okay? And in that case, EM and ER are in the same direction, and ER is longer than EM. We are longer, we are faster, okay? M is between E and R. Another way you could think about this would be to draw a little lines comparing the vector of ER to EM. So in this case, for instance, that is the length of ER, that is our, and I could compare that to the length of EM there, which is them. You can see that both our motion and their motion are in the same direction. However, we are going faster than them. Okay, great. So let's continue. Go on to the next case now. All right, this is here we are, and again we are north up, 12-mile scale. We're making 0, 0, 0 at 20 knots. So over here we can see there's our R and there's our M, 6 minutes apart, and we'll draw a relative motion line there. It looks like the relative motion is going 0, 0, 0. And if I really want to know exactly what it is, again, I could take that to the middle. I just drew it slightly off center so that you can see it quite easily alongside the heading line. So the direction of relative motion is 0, 0, 0. And the speed of relative motion, I would measure the distance from R to M. So I take that and I bring that over here. Okay, and it looks to me like that's 1 mile in 6 minutes. So I multiply that by 10. That gives me a speed of relative motion of 10 knots. Now, what's the CPA? CPA is going to be a line that is perpendicular to my relative motion line that goes through the center. So that's right there. And that, again, is going to be 7 miles, which you can see as I bring it over here to my scale. All right, and what's the TCPA? So I'm going to walk my distance now. That was 6 minutes, so I walk it again. Looks to me like the time of the CPA is going to be about 12 minutes, okay? So that's good. All right, now I got to do my true course and speed. So I'm going to apply my vector for my true course and speed, which is going to be 0, 0, 0. For 6 minutes, it's going to be 20. I'm going to move the decimal over 1. It's going to be 2. So I'm going to measure 2 here, okay? And I'm going to take that line now. I'm going to bring it towards R. I'm going to draw it there. I'm going to label this point E. And so now I've got ER and EM. Okay, and EM is them, so E to M, that is the direction. They are going 0, 0, 0, okay? And their true speed is going to be the magnitude of that times 10. So I measure this distance, I bring it over here to my scale, all right? And it looks to me like that green line is about 3 miles in 6 minutes. So if I multiply that by 10, it gives me a true speed of 30. So now, here I am. This is, again, there's no triangle. I just have a line, the triangle collapsed, that makes it a special case. And this is same course, but in this case, they're going faster. And since they're behind us, they are overtaking, okay? So EM and ER are in the same direction. EM is them, ER is our, and EM is longer than ER. They're faster than us. Therefore, they're overtaking us. Okay. And you could also think about this situation as R is between E and M. All right. And then you could also draw those lines again. All right. I'm going to draw a line here. ER, that's our. And I'm going to draw a vector here, EM, that's them. They're the same length. Okay, excuse me, they're the same direction, which means we're going the same direction, but theirs is about twice as long as ours. They're going about twice as fast as us. Well, a little bit less than twice as fast. Okay, all right, very good. So let's see what's next. Okay, so we got this situation now. So here is a point, maybe on our port quarter. All right, and that is where the target is at R, 0. And here's the target at 6M. Okay, and it looks like R and M are at the same spot. Okay, so the question becomes, what's the relative motion? Well, there is no relative motion. Okay, they're at the same spot that they were at 6 minutes ago. They're likely to be in that same spot 10 minutes from now, a day from now. Okay, as long as neither one of us changes our course and speed, they're going to remain at that same spot relative to us, which means there is no direction of relative motion. Okay, R and M are at the same spot, no relative motion, and there is no speed of relative motion. But there is a CPA. Okay, how far away from us were they at when at time 0? Well, they were 6 miles away. And how far are they away from us at time 6? Well, they're 6 miles away, which means their CPA is basically going to remain at 6 miles as long as we don't change course or speed and they don't change course or speed. So now the TCPA, well, you could express this a variety of ways, but we're just going to go ahead because it's at all moments. So we'll just go ahead and say, let's just go ahead and say 0. Okay. So, all right. Now, what's the true course and speed? Well, to get the true course and speed, I'm going to add in my motion. So I'm going 0, 0, 0 at 20 knots. So 6 minutes. I'm going to make 2 over here. I'm going to add that. I'm going to make this point E. So ER. Okay, and EM, look at that. We are E to R and they're E to M. That means same course, same speed. Okay, our vectors are in the same direction and they're the same magnitude. Therefore, we're the same course, same speed. Okay, so they're going 0, 0, 0. And if I measure the distance of that, it's the same distance I went in 6 miles, and that makes it 20 knots. This is no triangle. Again, this is a special case. Okay, same course, same speed. EM is the same as ER. And R and M are at the same spot. Okay, so and if I wanted to do it by that vector analysis, again, I would just draw my my little thing here, and I would say, oh, E to R, that's R. E to M, that's M. Look at that, same direction, same magnitude. Okay, great. So let's move on to the next slide. Okay, so this one is going to be here's R, here's M. Again, we're going 0, 0, 0 at 20 knots. This is the relative motion line, okay? And when I draw that and I bring it to the center, I get a relative motion of 180. So that's that. Speed of relative motion, I'm going to measure the distance between R and M, okay? And I'll bring that over here. And when I do that, it's 4 miles in 6 minutes. So 4, I move the decimal over. That gives me a speed of relative motion of 40 knots. Cool. So what's my CPA? Oh, I draw that line perpendicular to my relative motion line going through the center, and the CPA is right there. I can measure that over here. Again, it's 7. Okay. And what's the time CPA? I walk my line down. Okay. So that's 6 minutes. Looks to me like that's 12. I don't know. I'd say about 13 minutes. Okay. Now let's do our true motion. So I'm going to add in my motion. I'm going 0, 0, 0 at 20. So I'm going to put 2 miles in 6 minutes. I bring that to R. Okay, I'm going to label this point E. Okay, and we are ER, they are EM. And again, there's no triangle, it collapsed. This is a special case. So their direction is E to M. Okay, E to M. So they're going 180. And the speed that they're going, well, that's the distance they went in 6 minutes. I bring that over here. Okay. And they're going 2 miles in 6 minutes, which means their speed is 20. Okay, so they are on a reciprocal course. We're going to refer to this as meeting. Okay, reciprocal course for meeting. E and M is reciprocal. EM is reciprocal to our course, which is ER. Okay, E is between R and M. Lots of different ways you can think about this. Okay. The thing that's special about this is not the speed. It's only the direction. Their direction is 180 degrees to ours. Okay. And if I wanted to do that by the vector analysis, I would go ER, and then I would go EM, and I would see that those, we're going north, they're going south at 180 degrees to each other. That's a special case. Okay. What's the next slide? Okay, let's see here. We won't bother with that question. So here is R, there's M, and again, relative motion line right there. Our CPA will be, our direction of relative motion is 180. Okay, our speed of relative motion, I'm going to measure that distance, bring it over here. It's 2 miles in 6 minutes. That makes it 20 knots. So the CPA is that distance right there, okay, a line perpendicular to my direction of to my relative motion line, which should be about right there if I use my triangle to be careful. And that's about 7 miles. And the TCPA, so that's 6, so that should be about 12, 18, right? I walked that down. So I'm going to say it's about 25 minutes from whatever time R was. So if I took that at 2 o'clock in the afternoon, I would add 25 minutes, and it would be 14:25. I could tell the master of the vessel, the captain of the vessel, that, oh, the CPA of this vessel should be about 14:25. Okay, so 25 minutes after whatever time R was. So true course, true speed of the target. I'm going to add in my motion, okay, which is 2 miles in 6 minutes, since I'm making 20 knots. So I put that in here, okay, and there I put that there. That's great. So now they are E to M. Well, E and M are at the same spot. So their motion is E to M. Well, there was no motion from E to M. That means that there is no motion of that target. That means that target is like a buoy, or it's a vessel that is anchored, or it's somebody who's drifting, but there's no leeway, no current. Okay, those kinds of things. All right, or I'm in log W, but we'll worry about that later. Anyway, so that's no course, no speed. There's no triangle because they collapsed. So this is a special case called dead in the water. Okay, which is what we refer to that as. The direction of relative motion is reciprocal to ours. The speed of relative motion is equal to our speed. That's how you can recognize that. E and M are at the same position. Okay, and if I wanted to do my little analysis, I would go, well, E to R is that's our vector, and E to M, well, it didn't move. So they don't have anything. They're not making any motion. Okay, great. All right. And you could say that R, M, and EM are equal and opposite. Many different ways to think about this. All right, let's see what we have next. So the special cases. There's 5 special cases, and they're divided into 3 types. 3 of them are same course. Same course, target is overtaking us. Same course, we are overtaking the target. Same course and same speed as target. Okay, those are the first 3 observations we had. Then there's reciprocal course, which we'll also call meeting. Okay, that's when we're on opposite courses, but they could be faster, we could be faster. Okay, and then there is dead in the water when the vessel is, not moving. Okay, so those are the special cases, and here was a handout that we gave you in the lab as well. That's another look at that, okay, with the various vectors. And okay, so now we're going to talk about another situation. And this right here, we're going to consider that we are the burden vessel, and that we're going to, in this case, alter our course to avoid a collision or to increase our CPA to something that's more acceptable. So if a risk of collision exists, then one or both vessels are going to be burdened. If we're meeting, then we're both burdened. But if one vessel is on the starboard bow of the other, then that vessel is the burdened vessel. Okay, so if the vessel is on your starboard bow, you are the burdened vessel. If you're seeing their port light or red light, you are the burdened vessel. If they're seeing your green light, they are the stand-on vessel. Okay, so anyway, you may have to alter course, speed, or both in order to have a satisfactory CPA. To do this, you're going to need an existing ERM triangle that you have already plotted. Okay, And then you're going to need to know the CPA that you wish to create, okay, that you want a new CPA. You have a CPA that is undesirable. Maybe it's 0, maybe it's a half mile, maybe it's a mile, maybe you want 2 miles. So you're going to have to know that I want my CPA to be, different than what it is, what that value is. And you're going to have to decide when you're going to execute that that course change or speed change, okay? And so let's take a look at this. So we're back to the first image of that handout that I gave you, okay? This is back to that very first image there. And so here's a situation. We have a CPA of 0. The vessel is on our starboard bow. According to this aspect here, I'd be looking at this vessel's port light, and we're the burden vessel, okay? So here's what we're going to do. First thing we're going to do is we're going to decide if we're going to change course, speed, or both. And in this situation, we're just going to change course, okay? So I'm telling you what we're going to do here. We're going to determine what that new course to avoid the collision is, or the new course to alter to avoid the collision. And we're going to refer to that as the NCA. So the next thing we're going to try and do, or the next thing we have to do, is decide what is the new desired CPA. And oftentimes these are going to be in your standing orders or the master's verbal orders. So in this case, we're going to say we're going to use 2 nautical miles. So what I'm going to do here is I'm going to draw a circle. There happens to be one on here already that is at the desired CPA. Okay. Next thing I'm going to do is I'm going to have to decide at what point am I going to execute my change? What point am I going to make my course change? And we're going to call that point MX. In this case, I'm going to say, hey, let's do it when the target is 6 miles away from us. So, so when it moves along the RM to 6 miles, that's when I'm like, hey, that's close enough along that relative motion line. I want it to now go along a new relative motion line that's going to be 2 nautical miles, leading to a 2 nautical mile CPA. So what I'm going to do now is I'm going to take my triangle, okay? And by the way, when I draw this new line that I'm about to draw, this new relative motion line, this new desired relative motion line, this is my current relative motion line. I don't like it. The CPA is 0. I want a new relative motion line that's going to bring a CPA out to here. So I'm going to need a new line to show up from here to there. Now I could also draw the line from here to there, but that would be the vessel passing astern of me. I'm going to alter course. The vessel's I'm going to take their stern. They're going to pass across my bow. So the new relative motion line must cross my heading line, okay? So that means I'm going to do it here, and that is the new relative motion line that I want to see happen, okay? So, and by the way, if this is the new relative motion line, this will be the new CPA at 2 miles, perpendicular to my new relative motion line going through the center. So, great. All right, so what I'm going to do now is I need to start combining this new relative motion line with some of this information in this existing ERM triangle. I suppose I could bring this EM line down here, and I could bring my speed. Anyway, I think it's easier for us, okay, instead of creating a new triangle here, is to use the information that exists in our old triangle. Some of it is still pretty good, okay? Like, if we change our course, it's not going to change the course and speed of the target vessel at all, okay? But if we change our course, the direction of this line is going to change. But if our speed is the same, well, we're still going to be making 20 knots. I didn't say we're changing our speed. So the length of this line is valid. So there's a lot of really good information left over here. So let's actually take this line, this new relative motion line, and we're going to drift it. We're going to move it up into this ERM triangle, and we're going to do what you could refer to as a friend of mine, Captain Tunic, gave me this little saying. She called it the M&M hop, okay, or something like that. So we're going to hop the new relative motion line from MX to the old M, okay? So what I'm going to do is I'm going to use my triangle. I'm going to bring that up there, and that is the new relative motion line that I want. This is the old relative motion line, and this is what I want to have happen after I change my course. So now, this is the true course and speed of the target vessel, and this was my course and speed, okay, until I made my course change. Well, I'm making a course change, but I'm not making a speed change. And what does that mean? That means that the length of this line is still valid. However, I'm going to need to alter my course something to starboard. I'm going to be going in, instead of going in this direction, I'm going to be going somewhere over here. And I can figure that out exactly by swinging this line down until it intersects there. Okay? All right, so that is going to be a new direction, but the magnitude is still 2 miles in 6 minutes because I'm still going that speed. I'm going to label this spot right here R prime. Okay, all right. So that tells me this is a new R for a new direction. ER, our. This is our new direction. Okay, but our speed is the same. So if I want to know what that direction is, I'm going to put my triangle there, and I'm going to bring my triangle to the center. Okay, and this time I'm going in this direction. All right, so that would be if the new course is 040. If I was to alter course at an MX of 6, creating a desired CPA of 2 nautical miles. Okay, so that's that. All right, that's pretty good. So now, here is the question for you. What is the time of this new CPA? Okay, what is the time of this new CPA? All right, well, I'm going to need to go to my relative motion line to determine that. Okay, but in this case, I'm going to need to go to this relative motion line for part of the answer, and then this is the new relative motion line. So R to M was my relative motion line in the beginning up until MX, but after I change my course, there's going to be a new relative motion line. I'm going to need this relative motion line and the speed of that for the second part. So I need to combine both of these. So let's look. That's a lot of words. Let me just show you. That's how far I went in 6 minutes based on the old triangle. So that is, that's 6, 12 is about here. This is a little bit shy of that. So that looks to me like about 10 minutes. So from the time of R, 10 minutes is when I'm going to arrive at MX. That's when I'm going to change my course. As soon as I change my course, though, I'm going to have a new relative motion line with a new speed of relative motion, which is represented by this line R prime M. Okay, so now this is proportional to the speed of relative motion of the new line. So now I'm going to use that to go from here to there. So that is another 6 minutes. Okay, and that's 12 minutes, which means that's probably about 9 minutes. Okay, so the time for my CPA is 10 minutes using the old speed of relative motion and 9 minutes using the new speed of relative motion. I'm going to add those, and that's going to tell me that the new time of CPA, okay, with the course change will be about 19 minutes from the time of R. So if the observation of R is made at noon, okay, at 10 minutes past noon, I would make my course change, and at 19 minutes past noon, we would be at our CPA.